Greetings and welcome to a new video about operational amplifier circuits. In this example, we will discuss the negative feedback and the positive feedback together. We have discussed the negative feedback in more detail in the previous examples using the operational amplifier circuits to design amplifiers. We also discussed the positive feedback to design Schmitt triggers and other oscillator circuits. This time we will take this together and we will see how that affects our operational amplifier circuit and what kind of a gain we can get if we use these two effects, these two feedbacks together. So it will be a very interesting situation where we have the feedback both negative and positive. So it can be a little bit squarey. That's actually why I put this image here. So let's see how that works out in more detail in our discussion here. So the operational principle for this circuit, we will have the feedback conditions. Discussing actually this circuit here, we will see here 4 resistors, R1, R2, R3 and R4. You see here the 2 negative feedbacks and a positive feedback here, so that will be then actually the multiple feedback situation. So we have 2 feedback loops, 1 negative feedback, another one is positive feedback. And we have actually 3 conditions for this circuit. If you look at it, and we will designate here the node for the inverting input for the operational amplifier and also the non-inverting operational amplifier input. So if the inverting amplifier input, so this Vn node, is that larger than the Vp node, then the situation is negative feedback. Now, if you have that this is smaller, so this is larger, then you should have a positive feedback because the feedback for the positive part is then larger. But what happens if these two are equal to each other? That op-amp is actually operating in an open loop, so that means it will then rail to its maximum and a minimum power supply situation. We will see that how that works out in the simulation, and that means we don't have any net feedback for this third condition. Let's see the circuit analysis in more detail, and we just short this input here because that input can be also placed there. It is just arbitrary. Now if you look at this situation where you don't have an input, and again placing this Vn and Vp node, what happens here and in what condition do you have a negative feedback and a positive feedback in total? So analyze the effect of the component values on the feedback situation by setting the input voltage here to 0. Okay. So that means if you want to have a negative feedback, that means the Vn must be larger than Vp. That is the condition we just discussed. And for this, for negative feedback. And if you now go down, we can say a negative feedback here for this part. That means using voltage divider rule, we can say R1 divided by R1 plus R2 times the VO. Of course, considering the current in the op-amps are 0. That's the left part. And the right part is similar, then you do R3 over R3 plus R4, again voltage divider rule times the VO. Now we can now divide out the VO from the left and right hand side, so you get this equation. And now you need to consider this equation in more detail and to see what condition we need in order to have negative and positive feedback. Now we can do the cross multiplication, so R1 times the R3 plus R4, that's shown here. And also similar case, R3 times the summation of this R1 plus R2, that's shown here. So we will work out now the parentheses. You will get this result. Now you can remove the R1 times R3 from the left side and also from the right side. So the equation we get is pretty simple. You get now the product of R1 and R4 must be larger than R2 and R3 product. We can also write it down in a different form. You can say it is R4 over R3 must be larger than R2 over R1. That is the condition if you look at this circuit specifically to have a negative feedback. So this is an interesting result. Now if you now use this and look at the input versus output relationship, and again getting back to the input here, we can designate here the current I1 and the I2 and then develop the equation that relates the output to the input voltage. So we can use the Kirchhoff's current law here, again assuming the operational amplifier is ideal, so there is no current flow in this branch, in the non-inverting and inverting nodes. Then we can say I1 is equal to I2, and I1 is here, then Vi minus Vn over the R1, that's the left side. and then the I2 will be Vn minus Vo divided by R2, that's the right side. Again, cross multiplication, you see here again this part times R2 is equal to this part times R1. Now work out the parentheses, you see here the Vi times R2 and the minus Vn times R2. Similar case, we do that for the right side. And now collecting the terms, we will replace this part to the right side. You see that here. And collecting here the terms, so R1 plus R2 in the parentheses times Vn, that will result in this result. And you divide automatically also by R2, and you get now actually this expression. Now this is now the expression of Vi in terms of Vn and the output voltage using the resistors R1 and R2. But if you have also the voltage at the non-inverting input, that can be of course also used in this equation. Now that is just again voltage divider rule. So Vp is R3 over R3 plus R4 times the Vo. Let's designate this as equation number 1 and this as equation number 2. Now, if we use the condition that the Vn is equal to Vp, that is just at the edge of negative feedback, that means actually the following: for negative feedback, the operational amplifier tries to make these two nodes equal to each other. That is the job of the negative feedback. Now, if that is the case, that means this voltage Vp, which is expressed here in equation number 2, is also equal to Vn. So we can replace this here by equation number 2 here. So if you do that, and considering this condition, you have this expression for Vi, which is then the R1 plus R2 over R2 times, here this second equation, just replacing this Vn here, and then again minus R1 over R2 times Vo. Now we have an expression where you see all the resistors, R1 up to R4, and the input voltage and the output voltage only, which is exactly what we want. Of course, we need to massage this a little bit and get the result in a nice format like the Vo over Vi ratio. So what can we do? We can now take these two together in this format, and also this one here in the parentheses, and you take out the Vo. The next part is taking these two fractions in one fraction, so I can multiply this by R3 plus R4, of course also the numerator. That's actually what I do here. And I can now take this together here because they have now the same denominator. That's actually done here. So you see here Vi is equal to this part minus this part divided by the same denominator, so you just only take this here. Okay, now we can do the Vo over Vi by inverting this expression. So you flip actually the expression, you see actually the denominator will be numerator and here the numerator will be denominator. That's actually what I do. And I will now work out the parentheses here. I will just leave the numerator, but I will work out the denominator parentheses. So it is R1 times R3, also R2 times R3, and a similar case here. And I see now directly that some terms will disappear because I see here this will go and that will go, so I will lose them. And I have now this expression here divided by the R2 times R3 minus R1 times R4. I can even go further by dividing out the R2 from the numerator and denominator. That's actually shown here. Of course, I get a fraction here, but that is not really a problem. We will see that shortly. And I can also continue by dividing the R3 also. So again, divide the R3 from the numerator and denominator. I have now this expression. You see here 1 plus the R4 over R3. This will be 1, and then minus R1 over R2 times R4 over R3. Now we have this expression which relates the input and the output voltage. So this is a voltage gain expression where you see all the resistors. Now if we want to make the analysis easy, we can set R3 equal to R4. And then we have the following expression. That will be then 1 plus 1 is then divided by 1 minus. This is of course still the ratio we need to determine, and this is still 1, so that and that is then the expression we have. Of course, this is just 2, so that will be then 2 over 1 minus R1 over R2. Now you see here actually an interesting thing happening because the gain is really determined by the ratio of R1 and R2. Of course, taking these two together. And it can be positive, so that means in phase with your input, so the output voltage will be in phase with the input voltage. It can be also negative, so that we invert it because this can be 1 minus, for example, 4. Then you get here actually 2 over minus 3. So that can be an inverting gain. So you can switch from a non-inverting amplifier to an inverting amplifier. Okay, now let's now continue with the next analysis. We can make a table by looking at the ratio of R1 and R2. We just determined this is the voltage gain we have determined. You see here, it starts with 0 and then 0.2, 0.4 up to infinity. And this is the voltage gain formula from here. You see here at 0, which is the ratio here, then the gain should be 2, because then you get here 2 over 1 minus 0, which is then 2 over 1, which is gain is 2. Now if you increase this ratio, so 0.2, the gain will increase. If you make it 0.9, you get a gain of plus 20. Now if you make the gain, for example, 0.99, this will even increase. But if you get exactly 1, it's also mathematically here shown, you can see 2 over 1 minus 1, you should divide actually by 0, which is an error, which is undefined. So that's actually what we also see here in the table. And if you increase that further, so you get to 1.1, 1.2, etc., so you increase that further up to very large values, your gain will drop to 0. But now, after this 1, so 1.1, your gain will be minus 20, so it will be then inverting. So this part is non-inverting gain for these ratios for the R1 and R2, and that part here is all inverting. So the plot here, you see that in the red curve, it is actually shown here the ratio of R1 over R2 and the gain here, voltage gain in the vertical axis. And here, if the ratio is 1, that means if this is 1, you get an error, which is then an undefined region, where you see actually a hyperbolic function, which is going to infinite, and then getting back to the minus infinite, and then increasing like that. But it stays also here at this negative value. So it switched from the non-inverting to inverting, and it starts at the 2 as the gain here. Okay, let's now also look at the situation where we switched the input voltage, because it was before that the input was here. Let me go back, you see that actually more clearly. This was here, so the input voltage goes through R1 to the non-inverting input. I mean the inverting input of the operation amplifier. And if we now switch that, we can also do that like so, and then ground this part. So it's actually just flipped version. Now what happens here? Now again, we can analyze this by using the Kirchhoff's current law, so defining the currents I3 and I4. And these are equal to each other, of course, because there's no current flow in the operational amplifier branches, input branches. That will be then VI minus VP divided by R3 must be equal to VP minus VO over R4, which is I4, and that's shown here. Again, cross multiplication, similar action. So I go a little bit faster, and then let's again work out the parentheses, take out this to the right side, and again collect the terms and divide by R4. Each term you get actually this expression. Again, you see here an expression where you see the VI in terms of the output voltage and the voltage at this node, which is the non-inverting input of the operational amplifier. Now we can say the similar case as we done for the other input, then we can say the voltage at the inverting input here is then given by voltage divider rule, so R1 over R1 plus R2 times the VO. That is the Vn. So we can now designate again this as equation number 1 and this as equation number 2. Now for negative feedback, if that is the case, then these two node voltages must be equal to each other. So we can say this is also Vp. So we can replace this in here, and that's actually what we do here. And you see here now an expression again of input voltage, output voltage, and all the 4 resistors in this circuit. Now again, we can massage this by multiplying this R1 times this, and then R4 times this, and taking all together in the one parenthesis, and we have here this expression. We can move on again the similar fashion that we multiply this denominator by R1 plus R2, of course also the numerator here, and then taking this together here in this step. And we need to again flip this because we need to go to VO over VI, so that means the denominator will be numerator and numerator will be denominator. That's actually this action here. Again, we will work out here the parentheses in the denominator. So we will keep the numerator as it is, so R1 times R3, R1 times R4 in a similar case here. And you see here again, these two terms will cancel each other out, and that's actually what you get here. Now, getting to the expression in more detail, we can again say divide by R4 here and also here. That means also here. Now you get this expression. And you can also divide by R1, that is the next step, and then you get here 1 plus R2 over R1 divided by 1 minus R2 over R1 times R3 over R4, which is very similar to what we have seen when the input was here and the ground was there. Now if we set here the R1 is equal to R2, that's actually also shown here, then the gain expression will be 1 plus 1 over 1 minus 1 times the R3 over R4, which is actually shown here. And this is again very similar expression as we have seen it before for the other input signal. So again, the same situation. If the ratio changes R3 over R4, then the voltage gain can be inverted or positive, which is then in phase. It is non-inverted. Okay. Let's now take this here also and look at it in the ratio. This is really similar to the other example where you see again now the ratio, and it is now increasing from 0 up to infinite. And then at 1 we get an error, so then you get a switch from a non-inverting gain to an inverting gain. And this is again a plot similar to the other situation. Now the ratio here is R3 over R4, and this is the voltage gain on the vertical axis. It starts again at 2 as the gain, and then reaches the maximum at this error, and then switch directed to minus infinity, and then stays at the negative values, and then approaches 0 for the ratio, which is then here 0. I mean the infinite. Okay, let's now go to our design or discussion in more detail, and where we see also the simulation results. So we will discuss, that's our objective, we will discuss the effect of component values on our op-amp circuit having both negative and positive feedback. In this case we will use this circuit where we have the input here through resistor R1. We will set the R3 and R4 equal to each other. We will set them equal to 1 kilo ohm, and R2 is set here to 2 kilo ohm. So we will change actually the R1 here, and we will see the effect of that circuit. Okay, we will look at the calculations first. The voltage gain was given for this circuit by this expression in more detail. And we know that we need to take the R3 and R4 equal to each other. And this is then also taken here. The only unknown here is just R1. So we have then actually in total this expression. Or you can write it like so by multiplying the numerator and denominator by 2000. Then you have this expression, which is more convenient to work it out. Okay, let's first look at the simulation result, which is then the DC analysis. And we start first with the ideal operational amplifier. You see here the circuit in the SPI simulator. You see here the R3 and R4, both 1 kilo ohm. You see also the R2, 2 kilo ohm, and R1 is here changing. So what we do is the following. This is the output voltage, and this is the resistance R1 value. It starts at 0 and then goes up to 4 kilo ohms, and we see here the steps. And you see here that in blue what the output voltage will be. Now, if you have R1 is 0, you get here the 2 volts, which is of course what we also expect. By the way, the input voltage is here 1 volt, so to make the calculation easy, so we just actually multiply everything by 1, so you get directly also the V out. If you go to 400 ohms for the R1, then you get 2.5, and it's actually similar to what we have seen as the table. And we have here the error, which is then at 2 kilo ohms or 2000 ohm. That's also what we see here from this expression. So bringing up the table, you see here the R1 value from 0 up to 4000, and you see also here the output voltage with the input voltage of 1 volt. And you see again the error, which happens at 2000 ohm, which is of course the ratio of the R1 and R2. So this is also as expected, and we see also again the gain is positive for before we reach this error line, and after this error line the gain will be negative. Now what happens now if the situation is discussed using an actual operational amplifier model? In this case we take a TL081. Now the situation will change a lot. We have now the input again as 1 volt. Again we sweep our R1 here from 0 to 4 kilo ohms. So actually nothing changed, just the operational amplifier, and the operational amplifier is here powered by plus and minus 15 volts. You see actually that here. And this is the TL081 in the SPI simulator. Now what happens here? Now it starts at 2 volts because the input is still 1, so that is for R1 is 0 ohm the same, and R1 is 400 ohm. It's also VO is 2.5 volt. That's actually the same. But if you increase this, the resistor, the gain will, the output voltage will increase. But at some point it is actually getting to some maximum, which was not the case for the ideal operational amplifier. Why is that actually the case? So why do we have here the saturation region between 1.7 kilo ohm and up to 2.3 kilo ohm? Why is that? So why do we get this value? Why cannot we just go to infinite? Because the operational amplifier is also powered by a finite power supply, which is the 15 and minus 15 volts. So you might say, why don't we see this 15 volts also here? Because the operational amplifier will also consume some power. That means we don't get the full 15 volts at the output. So you will lose approximately 1.5, sometimes 2 volts for each direction of the power supply. That's why we have here this 13.3 volts approximately at 1.7 kilo ohm. You can, by the way, calculate that this is indeed the case, because if you look at this formula, you substitute here this 1.7 kilo ohm, and you get here 13.33 volt, actually, for this case, which is, of course, very close to what we see here. Now, if you now look also the other extreme, because if the resistor R1 is increased, so for example goes to 1.8 kilo ohm, then it drops dramatically to the negative rail, and then it stays there actually up to 2.3 kilo ohms, and then it starts to increase actually. So why is this staying at this level, and why is this not increasing right away? Because if you look at the value 2.3 kilo ohms, and again substitute that in this formula, and then using this 2300, you get here minus 13.33 volts, or the gain actually. Now this is also the maximum voltage what we can get. Again, we assume, or we use the input voltage as 1 volt. That's why we have also at the output minus 13.33, which is the maximum negative value we can get. That's why this is also getting up to this point leveled, and then if you increase this resistor further, so to 2.5K, 2.7K, then the gain drops, so we will also get here the line which is then increasing, so you get less negative. For 3 kilo ohms you get actually here minus 4 volts, you can calculate that also here. And for 4 kilo ohms for R1 you get here now minus 2 volts. So you see a clear distinction between the ideal and an actual operational amplifier model in the simulator. So you have to be careful with your input voltage. That will determine really the shape of this graph. So these are the actual maximum or saturation levels for operational amplifier. You have to be careful not to forget that. Again, here in summary, the table from 0 up to 4000 ohms, and from 1.7 kilo ohm up to 2.3 kilo ohm, here we get a saturated level for this circuit. So we have also seen that this is indeed correct, but for the limited case. Okay, well, let's also look at the situation for the DC analysis of our operational amplifier. Again, but now using the input as 10 millivolts. So we drop by 100 times. So it was before 1 volt, now it is 10 millivolts. What happens now? You see here again the gain stays actually for 0 ohms as 2, so you just double this, so 20 millivolts, that's correct. And then for 400 you can actually see that this is again 25 millivolts. So that's all correct, so it's actually the same gain. And now you see if we increase the R1 further, then we go to almost 2 kilo ohm, which is actually the edge for this peaking. So it is now 1996 ohms. You again approach this positive rail of your operational amplifier. If you go hair larger, so 1 ohm above, so 1997 ohm, then you go right away to the negative rail. In this case, you see the sharpness is, the peaks are really much sharper, and there's also not this saturation level anymore. There is of course a saturation here and saturation there, but it goes much faster, and then again gets to the inverting region for this circuit. So we have the saturation approximately at 2 kilo ohm, again looking at the formula. And here is the table for 0 up to 4000 ohms for R1, and these are the output voltages using an input voltage of 10 millivolts here. So what is the distinction difference between the previous discussion? If the input voltage drops, so you can change your input voltage, then your shape of your output voltage versus the R1 will also change. So again, according to the expectations also from this circuit. Okay, let's now go to the transient analysis using again the operational amplifier TL081 model. You see here the input voltage, which is a 1 volt peak, 100 Hertz signal, which is given here as sine 2200 pi t, so it is 100 Hertz. And you see here for different values for the R1, so R1 is 0, R1 is 1.5 kilo ohm, etc. You see different cases, and this is now the time, and this is now the output voltage here, and this is the input voltage. So what do we see? Now if the R1 is 0, you see here again it is in phase, so we get a non-inverting gain, which is then a gain of 2. If the R1 is 2 kilo ohm, you see a gain of 8, so which is again non-inverting, so plus 8. But if you make the R1 is 2 kilo ohm, you get actually here the railing, which is the saturating level. So this is a non-linear action for this circuit where the R1 is 2 kilo ohm. Now increasing the R1 to 3 kilo ohms, you get now an inverting action because this signal goes like so, and then you get an inverting action, and now the gain is -4. And for R1 is 4 kilo ohm, you get now a gain of -2, again inverted. So that you see clearly also in the time domain that the gain will go from positive to negative. Still the linear amplifications, there is no kind of Schmitt-Trigger or oscillator effect, but there is one problem or one issue you need to be considering. That is the R1 equal to 2000 in this case will give you an undefined situation where you see the operational amplifier is operating in the open loop condition. Again here the table in summary, so for R1 from 0 up to 4000 you see here the values, and for one situation you get the saturation. So again, according to calculations we have done here in this example. Alright, it was our video about the effect of the component values in an operational amplifier circuit where we have both negative and positive feedback. We have discussed in great detail how we can derive the voltage gain expression and use that to verify that also in the SPICE simulator, both in the DC analysis and the transient response. We also compared the ideal and the actual model in the SPICE simulator. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.